in your notes what the title is. So forming solids and symmetry. Okay, we're going to find the volume of solids when they are looking like this. So I have a little video for you guys to start. And you should take some notes on it, maybe a little bit.
By locating pairs of congruent. What is the true number of faces of a rectangular prism? In this lesson, you will learn how to analyze rectangular prisms by locating pairs of.
Hold on. All right. Yeah.
How can we represent three-dimensional figures in only two dimensions? In this lesson, you will learn how to represent three-dimensional figures with nets by analyzing their faces and bases. Because we are talking about three-dimensional figures, it's important that we understand what a dimension is. And I'm going to show you some examples of one-dimensional figures. Right here you see a ray, a line segment, and a line. And these have one dimension because they only have length. They don't have a width or a height. Two-dimensional figures have both length and width. A rectangle, for example, has a length and a width. So does a triangle, and actually all polygons are two-dimensional, or sometimes we might say 2D. You probably could guess then that a three-dimensional figure has three dimensions, a length, a width, and a height. Okay, we're going to jump into the core lesson, and we're first going to define what a net is. And a net is a two-dimensional pattern of a three-dimensional figure that can be folded to form that figure. So right here you see three different nets, and we're going to be exploring these over the course of the lesson.
So what would this make, you guys, if you folded it up? A cylinder. What would this one make? Rectangular prism. What would this one make? Good. So those are all called nets.
How might we create a net for a prism or a 3D figure like this one? The interesting thing about nets is sometimes there is more than one option of a net that matches up with a 3D figure. So all three of these nets could be folded up to form the prism that you see on the right. If you look closely at the nets, you see that each of them has 6 faces, and the prism also has 6 faces. Here is another illustration of a prism and its net. I want you to just watch closely so you can see sort of how the different faces correspond to each other. Right? 6 faces on the net, 6 faces on the prism, and as you can see on this image, 4 of the faces are purple, 2 of them are green. This is to help you understand a little bit more how the net might fold up to form a 3D solid. Okay, right now we're going to match the 3D figure that's going to appear in a moment to its appropriate net below. And we're going to do that by closely
your hand if you think it's C. All right, why is it not A? Yeah, how many triangles are on the blue figure? 2. How many triangles are on A? 4. 4. So A is actually a pyramid. If you folded that up, that would be a rectangular pyramid. It would meet at a point, right? B, okay, B actually works because how many rectangles are on the blue figure if you go around it? 3. So C has an extra one. It does not work. Can you guys tell if you folded that up, it would have like an extra flap, so it would not work. Okay? All right. So that's all I wanted to show you guys. Now I want to actually solve some of these. So the book's going to give you a net like this. So it's a 3-dimensional figure, but it's laid flat, right? So they like cut it up and laid it flat. So anybody know if we folded this up, if you visualize folding this up, what we call the figure? Ayla? Very good. Rectangular prism. And somebody walk up there and point to where the base is. Which part is the base when we find the volume? Morgan W. We could use that as the base, but I probably wouldn't. What do you think, Ayla? Nope. We could, but I wouldn't. Anya? Jayla? We're getting closer. Nope. Colton? Yeah. This and this would be the top and the bottom if you fold it, and this part would go like around it if you like folded it up, okay? So this is your base. So let's find the volume. You could. Yeah, it depends on you guys. It really, you could do any of them as the base, technically. But this is the easiest way to do it. Just trust me. Okay? Because those are the flaps, and everything else goes around. If you want to do this as the base, that's fine. But then you have to think through your height differently. This way is easier. But you can do it however you want, all right? So area of the base equals base times height. So just the base, so we're going to say the red pieces that I just shaded, are going to be 2 by 3. So this rectangle is 2 by 3, which is 6. So I'm going to plug that in for area of the base. Okay? If this is my base, what I just did here, then what's the height of the figure? 5. Good. So my answer is 30 inches cubed. Okay? If you want to do this as the base, what would you do for base times height? 5 times 3. And then what would the height of the figure be if you set that on the bottom? 2. Good. So you can do it that way. Now this one you cannot, there's only one option for what the base is. So somebody go up there and show me what the base is, Josh. Yes. You have to do the triangles as the base. The triangles are at the top and the bottom, or it doesn't really matter what side you set it on, but they have to be equal on both sides, and it's only the triangular base. So this time, the formula that we use for area of the base is the formula for a triangle. Then we're going to plug in 2 times 4 divided by 2. So we get 4 for the area of the base. And if the area of the base is 4, which is those triangles, what would the height be when we fold it all up? Monica? 8. Good. So that would be 32 inches cubed, because we're doing volume. All right, now let's talk about symmetry. So sketch that lovely thing. Okay. So symmetry, anybody know what symmetry means? Can anybody tell me? What do you guys think? Morgan? Yes. Good. Mirror image, or if you fold it in half, it's exactly on top of each other. Exactly on top of each other, right? So somebody come up here and show me where a line of symmetry is. Anya. Yeah. And point to a line of symmetry. Nice. Good. So we've got a line of symmetry right here. We could fold it in half. Kayla, go show me another line of symmetry. Very good. Right down the middle there, we have another line of symmetry. And anyone think there's another one? Could we do it across this way? No. It would not exactly fold on top of each other. It would like come off a little bit. So no. Those are the only two lines of symmetry. All right, now we have this like flowery sort of thing. So Jayla, come show me a line of symmetry. Okay. Sophia, come show me another line of symmetry. Okay, right down the middle there. Ayla, come show me another one. Okay, good. And Monica, show me another one. Nice. Are there any more? No. So this one actually has like 4 lines of symmetry, right? Is that 4? 1, 2, 3, 4. Yeah, 4 lines of symmetry. So you could fold it in a lot of places and it would fold onto itself. Yes, yes. A circle could. All right, are these figures symmetric about a point, a line, or both? So the first one is definitely symmetric about a line. Let's do the lines first on both of them. So Kaden, come up and show me where the line of symmetry is on this shape here. So where can I fold it in half and it folds onto itself? Not sure? Aaron, you got that? Good. Very good. Okay? And there's no other lines of symmetry. Now let's do lines of symmetry on the other one. Josh, B, what do you think? Is there a line of symmetry on the triangular thing here? Okay, go show us. There you go. Good. Okay, there's this one. Is there another one? Kaden?
Yes.
Good. We could also fold it there, and it would be a mirror image. All right. So symmetric about a point actually means that wherever we draw lines through it, so like right here, there's this point, right? Is this piece here equal to this piece here? Yes. It means it's symmetric about a point. Is this point here, or this distance here, symmetric to this distance here? Yeah. So this is equal here to here, and this is equal here to here. No matter where I draw a line, let's say I draw another line, it's not a line of symmetry. I just draw another line through the point, okay? No matter where I draw a line through the point, is the distance from the point to the figure the same here as it is here? Yes. Yeah. No matter where I draw a line, and it's not a line of symmetry, but just a line, I've got equal distances. So this actually means symmetric about a point. Okay, so you might make a note of that. No matter where you draw a line through that point of symmetry, there's equal measure from the point to the figure. Okay, this other one does not have symmetry about a point. Okay, we only could draw one line of symmetry, so that's your first. We've got that, but there's no point where no matter what, wherever I draw the line, it's going to be equal distance. Okay? All right, use symmetry to find the areas of these symmetric figures. Dimensions are in meters. So basically, we're using the fact that we know we have equal pieces to make it easier on ourselves to find the area. So I actually want to find the area inside each of these half circles. And notice that these are symmetric, right? So I want to find the area of that. How could I do it? Somebody give me a guess. Ayla? You could do 2 circles, right? Because if I put this circle right next to this one, it'd be one whole circle. And if I put this circle right next to this one, it would be one whole circle. So I would just do pi r squared and multiply my answer by 2. What's another way to do it? What if I did 1/2 circle? So I found the area of 1. Then what would we multiply by? Morgan? Yeah. Then you'd multiply by 4 because there's 4 of them. Are these the same formulas? Yeah, because 4 divided by 2 is 2. So however you want to do it, if you want to find 1/2 circle times by 4, or if you want to put them together and find 2 whole circles, that's fine. So let's do the 2 whole circles. I have 2 times pi times 5 times 5. You got it already? I think you're right, yeah? Oh, so you got 78 point for 25 times this. What'd you get? 78 point what? 6. I don't know. We should have someone double check here. Let's make sure. Somebody do 3.14 times 25 for me. Okay, so 78.5 times by 2, what is that? 157. Good. Okay, we need units. We are finding an area. Dimension is in meters, so meters squared. Okay. All right, now we've got this interesting figure over here. All right, it's sort of an S shape. What we're finding the area of is inside the S shape. So anybody have an idea, using symmetry, how we could do that? Morgan C., what do you think? Yeah, very good. We could actually make this into a donut, right? If we just like flip this around so it's on top, then we really have a donut where we want the outside. So what we're looking to do is the big circle, we could take the area of the whole entire big circle and then subtract out the little circle inside. So we're going to do pi r squared, and I'm going to use a capital R for the big circle, minus pi r squared, I'm going to use a small r for the small circle. Now, it's important that we find the correct radius. So the distance here is 2, but the distance of this little diameter is 2. So when you're doing the radius of the big circle, we're actually looking for here to here, this distance. Anybody know what that is? Morgan? Not 4. What do you think, Josh? 3. Because you got to split this diameter in half. It's 1, and then this is 2. So it makes it 3 for the radius of the big circle. Okay, minus the radius of the little circle is what? Oops. Anybody know what the radius of the little circle would be? 1. Good. All right, so 3 squared is 9. 1 squared is 1. Instead of multiplying 9 times pi and 1 times pi, what is 9 pi minus 1 pi? Right, so it's a little easier. Then we only have to do 3.14 times 8 one time. Anybody got it? What do you think? Okay, good. 25.12, again, meters squared, because we're doing area. All right, you guys, no whiteboards today.